Well, thank you so much. It's a real honor and a pleasure to be here. Before I begin my talk, I'd like to acknowledge my co-authors here. Chris Longeman, who is the all-around Modflow guru these days. He took over for Arlen Harbaugh, who was one of the original authors of Modflow. So Chris has been our new Arlen for many years now. And he's in some sense, the technical leader of our group. He really leads the direction of Modflow development. And then our colleague, one of the newer members of our group, Wes Bonelli, who is a fantastic software engineer and has done a lot of very valuable programming so far. And I know that he'll also make other contributions to Modflow development in the future. I'd also like to acknowledge the real particle tracking experts in this room, who include Professor Daniel Fernandez Garcia, my host, and Dr. Rodrigo Perez. Please join me in congratulating Dr. Perez one more time.
Thank you.
Well, and of course, I'm really grateful for everybody's hospitality, for making me feel so welcome my entire stay. Daniel, Rodrigo, Tere, Bea, Jesus, who's out there on the internet, and everyone else that I've met here. It's just been a fantastic experience. So the objectives of my talk are threefold. First, I'd like to describe to you briefly our two popular simulation codes that we developed in the USGS, and many of you are very familiar with these. Some of you in the room are more familiar with one of them than I am, I think. I'm not going to call anybody out by name, but I'm thinking of someone whose name begins with Rodrigo. That's Modflow 6, which is our groundwater flow and transport code, and ModPath 7, which is a particle tracking code that is compatible with Modflow 6 and other versions of it. I would also like to introduce and explain a new particle tracking model that we call PRT, that we are integrating right into Modflow 6, and explain how a new model like PRT fits into the object-oriented framework of Modflow 6. It's obviously good to know if you're developing for Modflow 6, but it's also handy to know if you're a user as well, just to understand how the code is structured. So let's start with Modflow 6, the groundwater flow and transport simulator. So Modflow's been around a long time, not as long as I have, but I think it was first released in 1984, and it's gone through many versions since then. The most recent version is Modflow 6, and the previous version before that was 2005. So all the versions up through 2005 used regular structured grids. And this is a bit simplified because you can have variations in topography, you can offset your cells vertically, but when you look at it from the top, it's rows and columns, and then it's layers as you look at it from the side. So layers, rows, and columns. And it could only simulate one single groundwater flow model. However, it was modular in design right from the start, so that you could attach various packages to represent different physics and different stresses on your groundwater system. And these packages were programmed so as to be largely independent, which made them easier to maintain, easier to add a new package. It just had to be designed with some forethought so that it would fit into this modular design. Now, the latest version of Modflow, Modflow 6, which came out in 2017, allows you to use unstructured grids. In other words, you're no longer constrained to that rectangular grid. And that's probably the most obvious thing you would notice. What perhaps is not as obvious is that it can support, within a single simulation, multiple flow models and multiple transport models that can all interact with each other. It too is modular in design, but now it's supported by object-oriented programming. So the way I like to think of it is that we've introduced an ordered complexity in order to avoid disordered complexity down the road that could result from just people adding things to the code willy-nilly, right? So we have this pre-planned structure that new pieces can fit into. So in Modflow 6, the cells are polygonal prisms. And you look at them from the top, they're polygons, and then these polygons are extruded vertically to form a 3D cell, and it has a flat top and a flat bottom. So our challenge in particle tracking is going to be go from particle tracking on a rectangle to particle tracking on a polygon. And it doesn't have to be a regular polygon, it just has to be convex. So here are just some examples of various grids that you can use with Modflow 6. Of course, rectangular with some cells, unused, inactive cells blocked out. And you could do this with pretty much any version of Modflow. But then Modflow 6 allows you to use triangular cells or hexagonal and arrange them in different configurations in terms of their connectivity. It doesn't have to be a regular matrix of layers, rows, and columns. These are all shown in 2D, but obviously you can have 3D mesh. You can also have nested grids naturally. There are a couple of different ways to do that. Triangular nested grids. This is an example of a quad-refined grid. So you start with a base grid that's regular, and then you can take a cell and chop it up into 4 equal smaller rectangles. And you can take one of those cells and subdivide that into even smaller rectangles. And you can just keep going level by level and keep refining. This is very useful for zooming in around features like wells or rivers, or something where you need that extra resolution. So in the old days, come on, we've all done this. You know what I'm going to say, right? This is how we did it in the old days. Right? Across. Okay, our well was here. So now we can avoid all that nonsense and zoom in on the well with quad refinement if we want to. So what we're working towards is something like this. Okay, this is a preview. This happens to be a Voronoi grid. It's got polygons and different shapes, different numbers of sides. And this was generated using a prototype of the algorithm that I'm going to describe to you today, the new algorithm. This is a Henry type problem, seawater intrusion, right? You probably recognize that. Fresh water is coming in this way, salt water is recirculating that way, discharging out there. And the red tracks are particle tracks. I tracked 3 different particles, one of them in the recirculating zone. And then these blue triangles are triangular subcells that I'm using in this new method that I'm going to describe to you. But that's just a preview of what we're aiming for here. But first, let's talk about what we already have. We have ModPath 7, which is a separate particle tracking code that works together with Modflow. Modflow provides the flows. ModPath uses those flows to compute particle trajectories. So you can do basically advective transport. It's good for looking at contributing areas, things like travel times, things like that. But one thing that Rodrigo has done is extend ModPath 7 to include, first he parallelized it, which makes it much faster because you can do, with independent particles, you can process them all in parallel, and that gives you much better performance. And also he introduced random walk. So not only can you do diffusion with not only can you do advective transport, you can also do diffusion on top of that with Rodrigo's version. So as I said, ModPath is a separate program from Modflow. It's compatible with various versions of Modflow, including Modflow 6, and it does particle tracking across rectangular cells, right? Each individual cell must be a rectangle, either in the context of a completely rectangular grid or with one of those quad-refined grids where we keep chopping rectangles into smaller rectangles. Now with Modflow 6, well, here's an example. These are ModPath 7 results on a regular grid. These are all squares. Right? And then over here, there's a quad refined grid where we've chopped the squares into smaller squares, and even smaller squares, and even smaller squares. So there are 3 levels of refinement. And we've zoomed in on the well. I think this is a forward tracking, what we call a forward tracking simulation, where you start particles and they just go forward in time. And some of them are captured by the well, some of them end up in a river. And this is a backward tracking simulation. We started particles at the well, and we're going backwards in time to see where they came from. And this is just zooming in on the quad refinement in case it was hard to see on the smaller picture. So you see these are the smallest cells here. So we want to be able to do things with arbitrary convex polygons, not just rectangles in Modflow 6. So I'm going to describe to you the approach that we came up with. There are obviously many different ways to do particle tracking across polygons or other shapes, but we had certain objectives in mind, and this is what we came up with. So our goals were to extend to basically generalize Pollock's method, which works on rectangular and quad refined meshes, and have it work on arbitrary unstructured Modflow grids. And we asked the question, how can we do this as straightforwardly as possible? So let's see what Pollock's method does. You have a rectangular cell, and Modflow has given you the normal flows across these faces. You know the porosity, you can translate those into velocities, right? So these are normal velocities of the flow going across these 4 faces. So what ModPath does is it does independent one-dimensional interpolations of the velocity from the x velocity from here to there, and the y velocity from here to there. So that defines a velocity field all through this cell. And that's what it uses to compute the trajectory of the particle. So as it turns out, because that's a relatively simple configuration, you can solve for that, for the exit time analytically. It's very simple, very elegant, very efficient. And that was devised by our colleague Dave Pollock, who's now retired from the USGS, but was there with us for a long time. So let's look at Pollock's method from another angle to set the stage for the new method. So again, we have our normal velocities on the rectangle. What we're going to do is define vertex velocities that are consistent in some sense with those normal velocities, those edge velocities, right? And this is not a brand new idea. I mean, the idea of vertex velocities and interpolating within a cell for particle tracking, and it's, for example, introduced by Hageland in 2007, and it's been incorporated into other work. So we're using it in this context here as well. And so green is what we're given, the green arrows, and the blue arrows is what we're trying to determine in such a way that they are consistent with the green arrows. And let me explain what I mean by consistent. If you look at this blue arrow in the upper left-hand corner, if you take the component of that vector that's normal to this face, it is consistent with this normal velocity. Likewise, if you take the component of this vector that's normal in the component, in the direction normal to this face, it is consistent with Modflow gave us for that normal velocity. So in that sense, these corner velocities are honoring what Modflow has told us the flows are. So we define the vertex velocities, and now we can interpolate between them, right? So we have, let's say we just focus on the lower triangle of this rectangle. We can interpolate these 3 velocities in space anywhere within this triangle. And we're going to do what's called barycentric interpolation. But it's basically, it's kind of like a ternary phase diagram, or if you're trying to, plot the composition of waters that have 3 different components and use like this ternary plot. It's the same sort of thing. Any point within this triangle represents some combination of percentages of the constituents that add up to 100%. So in our case, our constituents are the corner velocities. And we're just interpolating the velocity inside the cell as being some percentage of these constituent velocities. So, and obviously it's the same idea in the upper triangle. So it turns out that on a rectangle, this, if you do these two interpolations on the two triangles, you get an equivalent result to what you would have gotten from Pollock's interpolation, just directly on the rectangle. That was one of our goals, was to make this new method reduce down to Pollock's original method in the case of a rectangular grid. So this approach is consistent with that. She's skeptical, but trust me, I've checked it. So now we move to a convex polygon. So how are we going to handle this? Well, it's conceptually similar. Modflow essentially gives us these normal velocities on the edges. We're going to define vertex velocities that are consistent with these, just like we did on the rectangle. And we're going to chop up the polygon into triangles, and there are obviously many ways to do this, right? From pentagon, there are at least 5, and then if you introduce a center point, that's another way to do it. And we're going to use our barycentric interpolation to define the velocity field within each triangle. And each of these ideas is not brand new. These have been done before in the context of particle tracking. It's just the particular combination of these and the specifics of how we go about solving this is unique to this situation with Modflow. But there's a nice review by Zhang in 2012 in WRR that talks about various issues and reviews related work. So that's, if you're interested, that's a good paper to refer to. So we have our triangle, right? We've reduced the problem to tracking the particle across a triangle. It doesn't necessarily have to be a right triangle or any particular kind of triangle. But it makes things easier if we sort of put everything into a canonical form. So it's always the same, kind of dealing with the same, solving the same kind of problem in the same kind of coordinates every time. So we transform this into what we call barycentric coordinates. It's basically a skewed coordinate system. You know, this is one axis, that's the other axis, and we skew it so that this is a right triangle. Right, so some Jacobian does that transformation. And now we need to formulate the equations of the trajectory so that we can solve it and we know what the particle's doing. So we're going to solve for the trajectory analytically and then solve for the exit location and time numerically. That's going to be our strategy. So these are the equations, the ordinary differential equations that are coupled that describe the trajectory of the particle in 2 dimensions. There's also a 3rd dimension, but it's pretty much independent, so we're not going to worry about it. We're just worried about what's relevant to the polygon, right, in 2D. So we've transformed things from x, y into alpha, beta coordinates, but it's still linear. It's not linear. And so I've just written the equations. This is the alpha velocity, this is the beta velocity, and it's a function of position, alpha and beta, within that triangle. So it's just, again, we've got triangle vertex velocities, and there's a linear change in velocity as you move away from vertex 0. This way, that way. Any way you go, it's a linear change. Now, it turns out that we are formulating this canonical triangle such that this boundary always corresponds to an outer edge of the cell. So we've triangulated our cell into triangles. Some of these edges of the triangle are going to be interior. These are new lines that we've introduced in order to triangulate the cell. Some of these edges will be the original cell boundaries. So we always map it so that this bottom beta equals 0 boundary is one of the original cell boundaries. And what we assume at one of the original cell boundaries is that the flow that Modflow gave us is uniform all along that cell boundary. The reason we want to do that is, particularly in the case of a no-flow boundary, we don't want a variable velocity that averages out to zero. We want it to be zero all along that boundary. Otherwise, you could have a particle going in and out. It could leave the model when it shouldn't leave the model. Did you have a question?
I lost track of it. I'm worried about, like, I don't know if you know the work by Alexander Guillot, for example, with Michael Lenz and the Blues where they did for the bar scale training. And they had to modify the model because they had trouble near boundaries, especially when you had like two no-flow boundaries like that. If you straight up use Pollock, you have trouble. I don't remember.
Right. And I'm sorry, whose work was it?
It was Alexander Guillot during his PhD thesis with Michael Lenz and Philip Blues in Lebanon.
Okay,
It was pretty recent, like 20,
yeah.
I remember the details right now, but I was worried about this, like, whether you could handle no flow.
Yeah, basically that's our way.
Again?
So it's if it's zero, it's zero. If it's 5, it's 5. Is there a question online?
Yeah, well, it's when people speak from the floor, since they are behind the camera, we don't hear them. So if you could repeat the question, please. It would help.
Yeah, can you hear me, Jesus?
No, I don't think so. Okay, so the question was about, it was a reference to particular work that we believe was done in 2020 where they were trying to handle no-flow boundaries, and there was some, I guess like a singularity in where you had a corner of two edges coming together. We don't face that problem here. We're handling the no-flow boundary in a very simple way by insisting that the velocity that Modflow gave us is uniform all along an edge of a triangle that corresponds to one of the original cell edges. If that happens to be a no-flow boundary, it's going to be no-flow all along this edge, which is what we want. So particles can't be, if it's zero on average, a particle could actually escape that edge, which doesn't really make sense conceptually. Does that answer your question? That was Jesus, right?
Yes, thank you.
Okay. So because this velocity is uniform all along this edge, this is velocity, the beta velocity at vertex 0, beta velocity at vertex 1. These appear as a difference in this equation, so this term drops out. And that's good news, because now we partially decoupled our equations. Right? This is an equation only for beta. There's no alpha anymore. So that's great. We can solve for, we can solve for the beta coordinate as a function of time analytically, right? But we're still dealing with some complexity up there. What we do is once we solve for beta as a function of time, we can plug it in here and then solve for alpha as a function of time. So, you can take a system of two linear ordinary differential equations that are coupled, and you can do the general solution, right? And you get the eigenvalues in those cases. Are they real? Are they imaginary? Are they this and that? But basically, we've reduced it down to 5 specific cases. This is the nicest looking case, and this is the ugliest looking case. Right? Ugly in the sense of a lot of exponentials and crazy stuff going on. So we can always invert this to get t as a function of the beta coordinate, but we can't do the same with alpha. So we need to do a semi-analytical approach here. The way we're going to do this is we're going to identify an outflow interval for a particular edge, if there is one. Okay. So right now we're just considering this entire edge as an example. Right? These flows are going out. Particle might exit through this edge. We can further constrain the possible outflow interval using the properties of the beta coordinate as a function of time. And it's just, I won't describe the math here, but you can derive limits such that you can bound that outflow interval. So to understand what's going on here, it helps to have some understanding of American football. Unfortunately, nobody understands American football. But suffice to say that the particle is like a player who's carrying the ball and trying to advance that ball across the goal line to score points. We are like the defenders who are trying to intercept that player carrying the ball. So that's our job. And our defensive strategy is to keep that particle contained within certain bounds. Just like in American football, if a runner gets outside of the concentration of defenders, he has a better chance of eluding the defense. We don't want our trajectory to elude us. We want to keep it bounded, so we always know that it's within certain limits. All right, so we bracket the root. That's what we've done. We bracketed the root. And we're looking for a root of an equation where of alpha as a function of t equals 0. This is the alpha equals 0 face, which we're using as an example. All right, so in order to keep the root bracketed, a conservative approach is to use Brent's method, which is a combination of the secant method and bisection method, and it's guaranteed once you know the root is within certain bounds, it will never go outside of those bounds, right? As you're solving, as you're iterating, it's never going to go outside of those bounds. It's just going to keep narrowing those bounds. Now, it's slower than Newton-Raphson, right? But Newton-Raphson can lose the root unless it's guaranteed to converge if you start close enough. But what's close enough, right? We never know close enough. So Brent's method is guaranteed to work. So it keeps the root bracketed. So here's an example. Here's our Henry-like problem again. It's an unstructured Modflow 6 grid of Voronoi polygons, all different shapes and sizes. There's the diagram I showed you before with the triangular subcells. You can see these are the subcells that the track happened to pass through. And then here's just an animation of that, because it's nice to look at animations. So three different particles. Here's another example, a 3D grid with 3 layers. There's a well in the bottom layer, and there are constant heads right here. And I honestly can't remember whether this is going that way or that way. But here it is, sort of from an oblique 3D view. You can see the particles passing through the different layers of the model. That's just to show you, yes, we can do it in 3D. So how efficient is this method? So the semi-analytical solution I just described, how does it compare with, say, integrating numerically, right? Because you can just integrate this numerically and avoid all that nonsense. So I compared it with a 4th order Runge-Kutta, just for this example. And as we say, we like to compare apples to apples, right? We want to do the comparison on a fair basis, as fair as we can. So I tried to get a similar error in travel times, path length, or final location for these runs, just so, to make sure I wasn't giving an unfair advantage to one method or the other. And in my tests, which are admittedly preliminary, the Runge-Kutta took, 2.5 to 7 times as long for this particular example. So, it seems like this is promising in terms of efficiency, at least compared with numerical integration. But it's going to be slower than Pollock's original method, right? Because, that's about as sweet and efficient as you can get. Pollock's method is very elegant and very quick. But it can't do, arbitrary polygons. So that's the price you pay. So the pros of this method is that it is equivalent, from our point of view, it's equivalent to Pollock's method for rectangular meshes. So we thought it would be good if users, run the new method on one of their old models that has a rectangular mesh, and they've already done it with ModPath 7, that they would get the same answer, right? It doesn't have to work that way, but that's a desirable feature. It does respect the cell mass balance. can see Daniel.
It is divergence-free.
You know what's coming. But it does respect the cell mass balance that, the flows that Modflow gives us. It respects no flow boundaries and seems to be efficient based on our preliminary tests. Now, here we go. When I told Daniel the other day that it's not locally mass conservative, have you slept since then? By not locally mass conservative, I mean that when you break up the cell into subcells and you estimate the divergence of the flow on each of those individual subcells, ideally you want them to match the divergence of the cell overall. And the numerical estimate of the divergence would be you add up all the flows and divide by the area, right? So if you do that for the whole cell, and then you do it for each of the individual triangles, the divergences for the triangles would sum up to the divergence of the cell. But the individual triangles could be, if your cell is divergence-free, some of your triangles might have positive, some might have negative. And so they act as kind of like effective sources and sinks locally. Even though in the aggregate they conserve mass, but individually they can concentrate particles artificially or they can disperse particles artificially. And for reactive transport, that's not great, right? So, but Rodrigo and I think this can be overcome. Daniel, you're not so sure. And I think the key lies in additional corner velocities, giving us more degrees of freedom. Rather than one corner velocity per cell vertex, you can have two, so that adjacent triangles don't have to share one corner velocity. So the other problem is 180-degree angles. So again, we have this sharing of corner velocities, right? So say we have a quad-refined grid, for example. So there's a large square cell here, and that is adjacent to, say, another square cell that's been quad-refined. So it's connected to two smaller cells along one straight face, right? So this, if you imagine there's a vertex here, this is a 180-degree angle. The problem with that is that Modflow could give you this flow on this face and that flow on that face, and supposedly they're supposed to match here, right? Because it's 180 degrees. You're trying to choose a velocity vector that honors both this and that's impossible, right? So again, if we introduce more degrees of freedom, we give this, say this triangle its own vertex velocity here, and this triangle its own vertex velocity here. Then they don't have to share. And there's more. We have more sort of wiggle room to satisfy both of these constraints. So I think it's the same solution to both problems. And I've done some preliminary calculations that suggest it's possible. The trick is that it's easy to introduce more degrees of freedom. You just don't want too many. You can't, so that you can't close the problem, right? Otherwise, you're making arbitrary assumptions that just have no physical basis. So Zhang and others in 2012, the folks who did that nice review, they recognized that degenerate case, and they got around it by isoparametric mapping. But I think that would involve actually treating this as something like this as a quadrilateral, and then doing a mapping that maps it onto a square. And I'm not sure we want to go there, because then we're departing from our original triangulation. So the other question is, well, what is the best triangulation to do? What I'm doing currently is I'm interpolating things from these cell corners to the centroid and then triangulating. Is that the best way to do it? I don't know. It's certainly not the least number of triangles, because if you have a pentagon, there's only 3 triangles there. But there's 5 different configurations, right? So which one do you choose? And if I had a rational basis for choosing one of these over the others, I might go this way. But I don't want this to be like an arbitrary meshing decision that happened. And then if two people mesh their things, two different ways or whatever, they get different answers. I just want Modflow to give people the same answer each time, right? So now let's talk about the new particle tracking model for Modflow 6, which we call PRT, which incorporates this new algorithm that I just described. To see how that fits into Modflow 6, let's take a look at how Modflow 6 is conceptually organized. So these are the simulation components out of which a Modflow simulation is built. And it's all built on this object-oriented code design. So it's designed to be rather generic. The actual code that handles the setting up and the solution of these simulations and handling all these different components is written in a very generic way. So when Modflow is processing these different models, iterating to solve them over and over again and doing outer iterations, it doesn't need to know what kind of a model it is. That's pushed down to a lower level in the class structure, okay? That implementation is pushed down. But when you're looping over models or you're looping over packages within a model, it's done in a very generic way. And that's the benefit of the object-oriented design. You don't have to rewrite the same darn code over and over again, just with different package names or different model names, or different model types hardwired in, right? It can be done in a general way. So this is basically what you could do with any version of Modflow. There was no numerical solution component per se, but basically you have a simulation that included one single groundwater flow model. There was a temporal discretization and solved it somehow, linear solver, right? So in Modflow 6, you can also have a transport model. Previous versions of Modflow didn't do transport. Now we have GWT, which is a transport model. And that's a cell-based Eulerian solver for the advection dispersion equation. What Rodrigo is working on is sort of an alternative to that based on particle tracking. So you can do your transport using particle tracking, and that avoids most if not all of the numerical dispersion that you tend to see with the methods like the one that we have right now. Also in Modflow 6, you can have two groundwater flow models, or 3 or 4 or 12 if you want. And they can be coupled. They exchange information. So you can take a large model domain and do domain decomposition, chop it up. You have these exchanges where the different models meet, and they can exchange information such that you can solve them all together as if they were all one giant model. Or you can have a groundwater flow model coupled to a transport model. Again, these models are coupled through what we call an exchange. In this case, the exchange ultimately provides information on flows that is needed by the transport model. And if you're doing variable density simulation, then we also pass information about concentration, or we're developing a heat transport module also, so that would be temperature. And that can affect the density that you use in your flow simulation. So we have a simulation, a temporal discretization that applies to the entire simulation, all the models in the simulation. And then the models can be organized into solutions. So these are models that are kind of solved together in some sense. So in this case, there's only one model being solved in solution 1, another one that's solved in solution 2. But it can get a lot more complex than this. We originally had much more complicated diagrams than this, but they were almost incomprehensible. And so our new particle tracking model is just a new kind of model for Modflow 6. It's akin to, it's at the level of, say, the groundwater transport model, right? That's where it fits into the scheme of things. And because of the object-oriented design, it's relatively straightforward to plug in a new model like this. Now, my colleague, Wes Pinelli, who I acknowledged in the beginning, if he's listening, he's probably going, straightforward, yeah, right. It's been largely his job to wrestle with the straightforwardness of integrating PRT into Modflow. But, relatively speaking, it is straightforward. So in conclusion, we have this new particle tracking model that's being integrated right into Modflow 6. It's not a separate program like ModPath 7. The object-oriented design of Modflow 6 allows this to happen in a relatively straightforward way. Adding a new model is, you don't have to reinvent the wheel completely, right? There's sort of a template for doing it. There's an infrastructure for doing it. PRT includes a new tracking algorithm. That's, in some sense, a generalization of Pollock's original method, but it's designed for both structured and unstructured grids. This V is a particular type of Modflow unstructured grid that's defined by the vertices of the cells. And within this new model, there's a hierarchical design, which I didn't really describe in detail, but it allows you to, in a relatively straightforward way, plug in a new tracking method. So if in the end, Daniel, you're unsatisfied with the way in which we do or don't conserve mass, we can consider an alternative. The hard part will be just programming that alternative. Plugging it into Modflow is not going to be the major obstacle. Plugging into PRT is not going to be the major obstacle. So thank you very much for your attention. I'd be happy to answer any further questions.
Yes, thank you very much for your presentation. I have two questions. The first one, I saw when you were talking about structural grids, there was one which was called smoothing, I think, non-smoothing.
Oh, yeah.
Could you please?
Absolutely. So that has to do with it might be easier for me to just draw it. I can't find it. Yeah, why don't I just draw it? Okay. Can people online, can you see me here?
Yeah, if you switch on the line.
Okay. There it is. All right, so that has to do with how many levels of refinement you can have at a given, oh, sorry, Jordan, there you can have at a given interface, right? So you start here. And then you quad refine this cell, and you quad refine that cell. Okay, we're doing, at any given interface, there's only one level of refinement. So you can't have multiple levels of refinement, like, for example, like, right, can't have that many. You can only divide each thing into two. So that's what's meant by smoothing. So smoothing is eliminating, making sure you don't have more than one level of refinement going across any given interface.
So what local grid is the same as a local grid. It's kind of like a fractal grid.
Yeah, it's sort of like a fractal. You just keep zooming in, but you can't be too aggressive about chopping things up too quickly, right? You have to look one step at a time.
Thanks. And the second about the analytical solution for the particles.
Right.
So there was I saw that there was the exponential term, and I believe it was delta t. But I think you mentioned what the delta represents.
Oh, that, let me see. Very good. Oh, right, I went too far.
Yes, delta 1 and delta 2. I think you didn't mention what they represent.
Oh, I'm sorry. Those are just coefficients that come out of the solution. When you do the analytical solution, they're something. But they're functions of the original corner velocities.
Okay, so it's not, because I was confused with the Dirac delta. So
Yeah, no, I'm sorry. Yeah. No, those are just constants.
Okay.
Those are scalar constants.
Yeah, thanks for your talk. It's sort of a softball question.
I hope I can answer it now.
That's excellent. It's sort of strategic strategic. So it's cool to hear that Modflow is working on fully coupled heat flow and fluid flow. You've got the chemical transport and fluid flow. And then the, unstructured grid, it makes me wonder what's gonna happen to Sutra? Is there like an in-house competition? Can you speak a little to the long-term strategy about these two different codes?
There is still interest in Sutra within the organization. It's not at the level of priority that Modflow is, because Modflow is the centerpiece of what we call our enterprise capacity project. The idea is to create a modeling environment, if you will, where different models that adhere to certain protocols and certain standards can all play together seamlessly within, it's a dream, but relatively seamlessly within this environment. And so we would incorporate USGS codes into this and invite other institutions to also use our standard and so that these codes are relatively easily interoperable. You don't have to go in and mess with the Fortran there in order to couple two models together, right? It'll be much, because of input and output compatibility and things like that, it'll be more seamless. Less seamful, is it? Yeah, is that the same as more seamless? So that's the idea. So Modflow is definitely a high priority. Sutra's still alive. Hard to say what the future brings in the next 5-10 years. But there is interest in it, and we are about to release a new version that does freezing.
Yes.
Yeah. Yes.
So I think that you can say any of Pollock style approach without diffusion as well. You said, like, you no longer have the exit point.
Right.
I know that in these species, Rodrigo mentioned something about calculating the delta T, but I didn't ask at the time because there's a random term inside.
So my understanding is no, but I will defer to that.
So you can, these random terms you compute before the particle cross the interface. Once it crosses, you go back to the previous position, but you preserve the random term. It is included also in the calculation of the delta T.
So you sort of get exit point and correct for diffusion or something.
It includes both the advection and the diffusion. This last step is not aligning with the original exit point. Like it crosses, that the particle could be doing like a curve. You just calculate the exact exit point by considering both processes at the same.
Maybe we can talk about it so that it works in the detail, because I've thought about this before, but me and we've all thought it's kind of complex. So it'd be interesting to see if you can do. Sure. That makes a lot of difference. Then,
So for people online, I'm sorry I haven't been repeating the questions. Hopefully my answers to the previous questions kind of made the questions obvious. In this case, the question was, can you somehow preserve the essence of Pollock's method when you add something like Rodrigo's random walk on top of it? And so I think the answer was no, not really. You have to take a different approach, and Rodrigo has addressed this in his thesis.
if I have time, I'll just pick one more. Is there any hope? So I understand that this problem is a plague when you have some superstructure.
Yeah.
So my question to be naive is there a divergence relation scheme like equivalent to bilinear that you can use for triangles, since you know you always
Well, it's
have any points?
it's not that it's not the interpolation within the triangle that's so much the problem. It's the definition of the vertex velocities that results in a different. If I gave it the right vertex velocities for the triangle, it would be, it would give me the divergence I want. It's just that the way I'm setting up these vertex velocities, the divergence in the triangle doesn't match that of the cell. So that's the essential problem.
But you think you have a solution for this adding something?
I think so. I think adding more vectors. They say with 5 parameters you can fit a charging rhino. So
You can big.
yeah.
Thank you.
You're welcome.
I have a question concerning the moment you were talking, you were comparing it to a football.
Yes.
But technically, I got lost in what you said we're trying to maintain the between the two. But technically, what you do is you don't, I mean, it's not, you try to maintain it. But we know that if it's one of the two samples, I don't know, you know that, we know that it will directly, will or not, cross one or the other.
It's, well, those bounds are derived in a way that we know it has to be in between. If it crosses one of those boundaries,
Directly,
I've made a mathematical error.
Okay,
So, yeah, there's,
that's it. But you don't do anything to affect the trajectory. You were saying you try to maintain it.
oh, that's, yeah, oh, yeah. That's, yeah, that's, you're right. It doesn't affect the trajectory. It's just a matter of what we know about the trajectory. So, and what Brent's method does is it takes our original interval. We're confident that the solution's somewhere in that interval. We say, Brent, it's all yours. Right? And then Brent keeps narrowing it until it's within whatever tolerance we're happy with. But we know it's in, Brent will never adjust the interval such that the solution's outside of that interval. So it's always bracketed. So, which is, in terms of American football, it's a good strategy to keep the runner in the interior, right, near the middle where the defense is concentrated. Now, my understanding of soccer is even weaker than my understanding of American football. But there I understand you want to drive the offense to the outside, right? So, fundamental difference. Are there any other questions?
Maybe only.
Oh, yeah, are there any questions online?
Yes, actually, I do. I do have several questions. But perhaps to continue with the previous discussion, I think it would be nice to maintain the consistency with Pollock's method, even for random walk. The key issue here is whether you use the traditional Ito formulation for the random walk, or you use Stratanovich. But if you use Stratanovich, you can still be consistent. I mean, Pollock and random walk. Huh? So this is an ongoing discussion I have with Rodrigo. I don't think he cares, but anyway, this is a sort of a small disagreement. It's marginal. It's not so important. But the real question I wanted to ask, or a question or a comment, I'm not sure, is that this issue with the non-mass conservation inside the for each of the triangles. This issue was resolved by Kortz and Kinselbach. I'm not sure if you're familiar with the work of Kortz and Kinselbach. This is pretty old, maybe 30 years ago.
Yeah, they're looking at elements, right?
Yeah, the key is, Martin is familiar because Martin programmed it in our group. So you might ask Martin for the details. But the key issue there was that in addition to impose the type of interpolation that you are doing, they imposed that the resulting heads were irrotational. So yeah, the gradient of head, because it's a gradient, it should be irrotational. I mean non-rotational, and that helped a lot. So I wonder if you have given any thought about this. Otherwise, we might, I don't know, explore that option. There is a degree of arbitrariness, and you mentioned it, on the way you triangularize and on the way you define the vertex velocities. So you can at least limit that degree of arbitrariness by imposing the non-rotationality condition.
Yeah, yeah, that's a tough question to answer. There's also the issue of whether we really expect the flow to be irrotational, because if it's
no, the point is
isotropic,
the non-rotational condition. they impose on the gradient of head, not, I mean, on head, yeah, the field that is irrotational is the gradient of head, not the flux. The flux may be rotational in the, like in the case of density.
Okay. Yeah, I'll have to take another look at that. Thank you for that suggestion. I'm afraid I can't.
I will send you that link.
So we'll certainly consider any and all approaches to get over this problem. Yeah, thank you, Jesus. Are there any other questions online or in the room? Oh, I see, I could have seen you, Jesus, if I looked to my right.
Right behind you.
Or behind, oh, there you go. Right,
So, just one quick question. Well, thank you in the first place for a great seminar. For the C coordinate, the set coordinate, to keep the original color method. That at least all of these approach applies only to the horizontal plane.
That's right.
Because you always have like prism style cells, right?
Yeah, it's always flat tops and bottoms, so it's easy. All right.
Okay.
Thank you very, very much for this opportunity.
Thanks to you. Very nice presentation.